Welcome students to this video, and in this video we are going to talk about first order equations. So essentially we have already discussed that a general first order equation will look like this, right? It's some function of x, y and then z. Of course z in this case will be u, so maybe I can write it as u, and then we have ux and uy equals to 0, right? So this is basically a general form of a first order equation, right? First order equation, sorry, in two variables, yeah. Of course, if you make it 3 variable or 4 variable, you just have to add a ux, uy, uz, uw and so on and so forth. Okay, here one of the things which we need is and at least f with respect to p or f with respect to q is not 0, where we are saying that p we are denoting it by u of x and q we are denoting it by u of y. So basically what I am saying is this: f with respect to this variable or with respect to this variable, either one of them has to be non-zero, okay, so that it guarantees that this is going to be a second order equation. And of course this, where is this xy of course will be in some domain D, which will be part of R2. I hope this is clear. Now in this part also, what we are going to do is basically this is a second order first order equation, right, in two variables. But the thing is, and it can be a non-linear equation per se, but the thing is there is a difference. So basically you see, up till now we talked about a linear equation, right? In the other videos, earlier videos, we talked about linear equations. So this equation can be a linear equation. So basically, for example, let's say it may look like this, right? Ux plus uy equals to 0. Okay, now it may also be a non-linear equation. So what is a non-linear equation? The definition which I wrote earlier was a very general definition, in the sense that, I mean, if you are looking at something like this, let's say ux plus uy equals to 0. So this is an example of non-linear equation in that sense. But the thing is this, you see, while solving this sort of problem, the difference between linear and non-linear equations, or non-linear equations, can be this also: ux plus uy square equals to 0. So basically non-linear with respect to the u variable. But the thing is, you see, the idea is we need to solve this problem, right? So between linear and non-linear equation, there are like other two classifications which you can make, and basically the degree of difficulties of solving is increasing with every step. So basically, first of all, we'll define something called a semi-linear equation. Okay, so semi-linear. So you see, linear equations are the most easy equations, okay, to solve essentially. And after that, we are going to what we are going to do is we are going to define something called a semi-linear equation. Yeah, and we are doing it for a first order equation. Yes, it can be done for a second order equation also, but for now we are just taking it with the first order. Okay, so what sort of equations are we looking at for the semi-linear equation? So basically you will look at this sort of problem: a of xy, u of x plus b of xy, u of y. Okay, now the thing is, you see, with respect to the derivatives of u, this should be always linear. Yes, but then what happens is, with respect to the other part, so basically the part which contains u, x, y, those parts, it can be non-linear. So basically this should look like this: c of x, y and u. Yeah, now c is an arbitrary function. Yes, c can be any function. So if you have this sort of form, we call such a equation as a semi-linear equation. Yes, okay. Of course here we are assuming that either one of them. So basically, or maybe you can put it like this in mathematical terms: a square plus b square not equals to 0. Okay, now what is a square plus b square? A is this and this. So a of xy square plus b of xy square, I'm just writing it like this. What it guarantees is at least one of the coefficients ux or uy exist. That's the thing. Okay, So that's your semi-linear equation. Now the thing is, as an example, you can look at it. You see, it looks very much like a linear equation in the highest order. That's basically it. Okay. So the first example, let's just say, stick with this. Let's say y ux plus x square uy equals to, let's say, I don't know, maybe we can put it like u square plus x square plus y square. Yeah? So this is an example of semilinear equation. See, the thing is this is a nonlinear term, but nonlinear in x. We are not really interested in that. We want the nonlinearity. So we want linearity with respect to the highest order. You see, the highest order of u here is contains ux and uy, right? But ux and uy are both linear this thing terms. So this is a semilinear equation. We don't really care about what happens with x, y and u. So those can be nonlinear. So this is a semilinear equation, and the point is this equation is a, of course, you see, since this nonlinear term u square is there, it is not as easy as solving a linear equation. Should not be, right? That's the general, I mean, intuition. But the thing is it will again not be as difficult as solving a equation which is nonlinear with respect to the derivatives, you know, ux and uy, that sort of thing. Okay, right. So let's look at another example. Let me give you another example. So let's say ux plus some constant, or maybe uy plus u square equals to 0, or u to the power 5 equals to 0. So again, this is also a semi-linear equation. You see, it is linear with respect to the highest orders, and then it can be non-linear. We do not have an issue with that. Okay, right. So now, as I told you, between linear, so essentially what we have initially in the earlier videos, we talked about there is something called a linear equation, and then there is something called a non-linear equation. Okay, so that is a broad classification actually. Yeah, with that classification, actually the semi-linear equation is also non-linear. Yeah, because this, you know, it contains this nonlinear terms in u. But the thing is this, for solving solving this problem between these two, we are just putting two more. So one is a semi-linear equation. So as I told you, semi-linear equations are equations which are linear with respect to the highest order derivative terms. Okay, so and they are actually difficult, slightly difficult than linear equations. Okay, so linear equations are the most easy one. So this is like a easy thing. Yeah, so easy to hard. See, linear equations are easy to solve. After that you have semi-linear equation, then you will have a something called a quasi-linear equation. Okay, quasi-linear equation, this is a fairly harder problem than semi-linear equation, and of course after quasi-linear we will have a non-linear equation, which is the hardest of them all. Okay, so what is a quasi-linear equation? Let's just look at it. Quasi-linear equation, so what is it? Basically it will look very much like a semi-linear equation, except the fact that this a can be a function of u also. So a earlier was a function of x and y, here it can be the function of u also. Okay, so it should look like this. So b of x y u u of y equals to c of x y u. Okay, see now with respect to the highest order, okay, so basically here ux or ui, right, the derivative, the coefficient of it can contain u but not ux or ui. Is it okay? So essentially if it looks like that, then we call it a semi-linear equation. Okay, let me give you one example, maybe, or maybe two example, doesn't matter. Let's start with one example. Okay, so you see, if you have ux plus uy equals to 0, y equals to 0. Okay, that's a semi-linear equation, because you do realize in this case what is a is essentially a of x y u is u and b is 1. So that's your semi-linear quasi-linear equation. Okay, right. Let me give you another example, maybe. So let's take it this way: u x plus u square uy. This is also so equals to, let's say, something 2y. That is not a very important thing. Whatever it is there, that will be your c. This is your c. Okay, so you do realize, you see here, this is your b. So it can be nonlinear with respect to u also, but the thing is, it should not contain any term with ux or uy. Okay, so this is a quasi-linear equation. You do realize just by looking at it. So let's say here, let me put 0. So by looking at it, you do realize that I mean it looks much more complicated than semi-linear equation, and definitely much more than linear equation. But of course, non-linear will look like this, right? So basically, in this case, non-linear equation, we are basically going to tell that if the coefficient contains the coefficients of ux and uy should contain I mean ux and uy, those terms should be there at least. Okay, so in that case they are non-linear. So in this thing, what we are going to say is anything which is not quasi-linear or semi-linear or linear, those are non-linear. Is it okay? So that's the definition which we are going to stick with for this. Okay, so with this, what we are going to do is, first of all, we start with the construction of first order equation. So you will have some idea of how all of this is coming. Construction of first order. Okay, so what we have is this. Initially, we are going to start with a geometric surface. Okay, it's a system of geometric surface. Okay, so let's start with a system of geometric system of surface essentially. Yeah? Geometric means surface, system of surface, and is given by, which will be given by some capital small f of x, y, z, a, b equals to 0. Okay, where a, b are the parameters. Okay, these are arbitrary parameters essentially. Arbitrary parameters. Now what happens is, you see, once you have something like this, and f is C1. So basically what I am trying to say is this: it is smooth with respect to all the variables x, y, z, a and b. Is this fine? Now the thing is this, see, what we can do is, since this is smooth, let's just call it 1. So since f is smooth, we can talk about the differentiation of this thing. So basically we can differentiate this whole expression with respect to x and with respect to y. So once you differentiate it, what happens is we have fx of x, y, z, a, b. I am not writing it like this, plus so basically you have to, I hope you know the derivative of this thing. So basically f is a function from, if you think about it, it's basically r3 to r, right? A and b are parameters, so you don't have to worry about it. Okay, r3 to r. And so essentially, if you want to take the derivative of f with respect to x, essentially that will be gradient of f, and then the I mean the derivative with respect to x, which is 1, derivative with respect to y, which is 0, derivative with respect to z, which is z of x. Okay, because z is a function of x and y, remember. So here I am assuming that z is a function of x and y. So basically that is your u. Okay, function of x and y. So z is u essentially, yeah, but I am writing it z. Okay, so here what happens, if I am taking the I am differentiating 1 with respect to x, it becomes f of x, gradient of f, right? See, gradient of f is fx, fy, fz, and then you have this dot product 1, 0 and zx. Zx is, we'll call it as p. Is it okay? Okay, so it becomes fx plus p fz equals to 0, where p is nothing but your what did I tell you, zx. Okay, and if you differentiate the thing again with respect to y, we are going to get the same thing, except x will be replaced by y, and then p will be replaced by q. So this becomes f of z equals to 0, where q is z of y. I hope this is clear. Okay, so this is differentiating this relation 1 with respect to x and y. Okay, now the thing is this, you see, we have a system, I mean we have some relations. So the first relation is of course there, and then you have this second relation, and you have this third relation. Okay, and these three relations, so you see the set of three equations, actually the set of three equations, okay, involves two parameters a and b. Meters a and B. Okay, two parameters are A and B, and there are three equations. So generally what happens is this, I mean, you can actually eliminate those two parameters and then you end up with some equation. So eliminating A and B, eliminating A and B, one gets a relation like this: f of x, y, z, and then p, q equals to 0. I hope you understood what's happening, right? See, 2 and 3 we got it from 1 by differentiating with respect to x and y. 1 is a relation which contains a and b. Now you have three different relations and you have two parameters which you need to eliminate. Once you do that, what happens is you end up getting a relation containing x, y, z, p and q. Okay, so this is your so basically this system, this surface, the surface that actually gives rise to this first order PDE. Okay, so basically in conclusion, let me put it this way. Conclusion, so the system of surface, or you can say the surface actually gives rise to a first order equation. Okay, right. And of course vice versa is also true. Basically, if you have a first order equation and let's say if you can solve it, you actually end up getting a relation like that, like 1. Okay, right. So what we have is the C. So okay, in this case what happens, if you have a first order equation, so we went from here to here, right? We have a surface, and after eliminating the two parameters we end up getting this relation which is capital F of x, y, z, p, q, and f is sufficiently smooth. Okay, now what happens is, if you are given an equation like this, let's call this 4. If you are given a first order equation like 4, and if you somehow, let's say, yes, can solve the equation. Okay, so you see, you actually going from here to here. If you do that, then what happens is you end up getting two arbitrary parameters, right? Okay, and this particular form, the one, is called the complete solution or complete integral of 4. Okay, so 1 is called the complete solution, okay, or sometimes it is also called the integral, complete integral of 4. Yes, this is very clear. So given a surface we get a first order equation, and again given a first order equation, I mean, please don't think that we can always do this, but if you can solve it, let's say, then that will contain two arbitrary parameters, and then that will be called a complete solution of the relation 4. Is it okay? Right. So with that, let's just look at one problem, and then we will figure out what exactly is happening in this part. So let's say you have a family of spheres. See, initially what did we do? We started with a family of surfaces. Sphere is a surface. So I said system of surface. So basically that's a family of surfaces, essentially same thing. So we start with this family of surface. How does it look like? It looks like this. See, x square plus y square plus z minus c square equals to r square. Is it okay? And of course you do realize that's a family, because the thing is, C is of course fixed, and this is a sphere, right, with center 0 0 C and radius r. So the r is changing essentially. Yes, of course in this case C is also, so basically if you think about it, C is also a parameter. See, 0 0 C, I'm saying C if you put a particular value of C, it's fixed, but the thing is here C can take other values also, right? Yeah, so in this case C and R are parameters. So C and R are two parameters. Okay, right. So once you have this, what we need to do is we need to find out if we can get a system of equation, first order PDE corresponding to this family of spheres. Okay, what do we do? You remember, once we are given this relation, so this is your small f. So in this case, what is our small f? F of x, y, z, and then C and R, right? In this case, C and R. Initially we started with AB, but in this case C and R, it will look like this: x square plus y square plus z minus c square minus r square. Is it okay? So that's equals to 0. Now we have to do what? Initially, you remember, to get 2 and 3, we differentiate with respect to x and differentiate with respect to y. The first relation is fx plus p fz equals to 0. So if you have, so therefore, what is fx plus p fz equals to 0? That's your first relation. So what is fx in this case? It is 2x, okay, plus p. P is, you remember, p is zx, you see, zx, okay. So p, so here p is zx, if you remember, plus p fz, and now if you are taking this with respect to z, so it becomes z minus c, yeah, that is going to be 0. So essentially you can cancel this 2 out, so it becomes x plus p z minus c equals to 0. And similarly you have fy plus q fz equals to 0, yeah. So if you solve that, that becomes y plus q z minus c equals to 0. So here q is z with respect to y. Is it okay? Now what we have is from these two relations, so let's call it I don't know, maybe initially we had 4, right? So let's call it 5 and let's call it 6. Okay, so from 5, 6, and let's call this thing star. One has, okay, what do you have? See here, from this relation you are going to get z is x by minus p, and from 5, from 6 we are getting z minus c is y by q. So from 5 and 6, what do you get? X by x by p, right? Minus x by p equals to minus y by q. So minus y by q. So that will give you qx minus py. This is going to be 0. Yeah, we don't need the first relation star in this case, because I mean without that only we can just eliminate everything. Yeah, so you see in this case we have this thing. This is a I mean equation which is a first order equation. Okay, so you see this is your first order equation. So this is how you construct first order equation basically. Yes, first order equation. Okay, so I hope you understood what's happening here. See, if I'm given a family of some surfaces, in this case a sphere, what happens is by taking writing it like a small f of some variables, what we do is we differentiate with respect to x and y. We get 3 relations out of it, and once what happens is, in this case, in our particular case, we really didn't need relations, but the thing is here 2 relations was enough to actually eliminate both the coefficients c and r, right? You see, both the coefficients c and r can be eliminated, and once you do that, you end up getting a first order equation. I hope this is clear. Okay, so now what happens is this. Let's just look at another problem. Yes, let's say that maybe I can, okay, this is A, this is B. Yeah? I want you to do this problem by yourself. Okay, I'm not going to solve this problem. I want you to do it yourself. Okay, so find the PDE, okay, first order PDE, of course, corresponding to the surface, corresponding to the surface. So basically this is a family of surfaces. I'm not writing like that, I'm just writing corresponding to the surface, x minus a square. So again this is a sphere, yes, plus y minus b square plus z square, okay, equals to r square in this case. Yeah, So I mean, try and find out if you can do that. What is the family of surface? So in this case, you just stick with this thing. You see, a and b are the two parameters which are dependent here. Okay, just that. Okay, right. So try to find it. Now the thing is this, we finish this particular video with a small theorem. This theorem, most of the proof is very easy. I just want you to finish the proof. I will just write down the theorem and give you what exactly you need to do here. So essentially, let's say if you have two functions phi, the first function phi is phi of x, y, z, three variable function, and you have another function psi. Psi is a function of again x, y, z. Okay, so let's say these are two given functions, we don't know whether these things are there or not. These are just given functions. Okay, now, and it is also said that f of phi psi, this is going to be 0. Let's say it is given, yeah, for an arbitrary smooth f. Okay, so essentially what happens is you start with two functions which are functions of three variables, yeah, and you also look at a relation which depends on those two variables. Yeah, the relation is f equals to 0. Essentially you are looking for that sort of label set. Okay, now the thing is this, then z, which is a function of x and y. Okay, so this satisfies a first order PDE given by, what is the first order PDE? It is given by this P. Okay, and let me put it this way. Maybe I can put the Jacobian part. Okay, let me put it this way. Delta of phi psi by delta with respect to P, right? So this is yz plus Q del of phi psi del of, this is Q, right? So this is z and x equals to del of phi psi by, this is nothing is there, so it is x and y. Is okay. So this is the thing where this notation del of phi psi by del of x and y, it means phi x, phi y, and then psi x, psi y. Okay, so let me just quickly give you the proof of this thing. The proof is very easy. Okay, so basically what this is saying is this: you are given a relation which is like this, f of phi and psi equals to 0. Okay, and what it is saying is this, then the thing is this, you see this phi and psi, these are two functions of x, y and z, right? If something like this happens, then you can say that the z, okay, will be a function of x and y. Z, which is a function of x and y, it will satisfy this particular first order PDE. Yeah, you see this will be basically some functions. Okay, these are basically functions, and then PQ, these will be your ux, zx and zy. Okay, so where this P is zx and Q is zy. So you do realize this is a first order PDE. Okay, so once again, okay, fine, let's look at the proof of it. So the proof is very easy. See, since f of phi psi is equals to 0, right? That's what given to us. So we can take the derivative. Yes. Now what you do is this. See, this is a chain rule problem, yeah. And the thing is this: some of you may not be very comfortable with this chain rule thing. So what I am going to do is I am going to write it down properly so you know what is happening here. Okay. So this is the relation given. So let's just call it star, double star. This is a given relation. I want to do a differentiation of this thing with respect to x and y. Is it okay? So how do I do it? First of all, you write it like this. So define g of x, y, z. Okay. So this is the idea. You define it like f of phi, which is a function of xyz, and psi, which is a function of xyz. Okay, so basically this double star is g is equals to 0. That's what is given. Okay, now if this is given to us, what is g of x? Let's just look at it. G of xyz, this will be nothing but f of phi x plus f of psi x. This is just chain rule, right? Yeah. So basically this is gradient of f and then phi x and psi x dot. So which actually turns out to be this particular thing. And if you look at what is gy of xyz, what does that gives you? It is basically f phi of phi y plus f psi of psi y. Is it okay? So those two relations are there. Now you see, if sorry, what I am missing something? No, okay. So f is equals to 0 given. Okay, so if g is this, you see, if I am defining, so if I am defining g to be this, so gx equals to this is going to be 0, and then gy which is this is also 0. Okay, so we'll do that, but first let me just write it down with respect to z. Now you see, if I am taking gz with respect to x, y and z, and so that will be give us phi x f phi and then phi z plus f psi and then psi psi z. Yes, okay, so that will be nothing but p times f phi plus q times f psi. Yes, fine. Now what you do is, you see, the thing is, if you put all of this this three relation together, maybe I can put it like 1 2 and 1 2 3. Okay, so you see gx is going to be 0 because g is 0 essentially. From double star, g is going to be 0, so gx is going to be 0, gy is going to be 0, gz is going to be 0. Okay, so if you put all of this together, what happens is this. Let me put everything together. What you are going to get is f of phi, okay, and then phi of x plus p phi of z plus f of phi, okay, and then phi of x plus p phi of z is equals to 0. I should get this thing. Yeah, so please do this calculation. It's not very difficult to do. You see, these two term will be adding up. Okay, and then the other two term you have to multiply it by p and then put it together. Yes, okay, so you have this relation, and similarly you also have this relation f of phi with respect to y. Now it is phi of y plus q phi of z plus f of phi and then phi of y plus q phi of z is equals to 0. Yeah, so just by looking at the relation, you do realize, you see, just by adding and multiplying p, you are actually ending up getting that particular thing. Okay, so these two relation. Now you see, we want a non-trivial solution for phi x, f phi and f psi. Okay, now since for non-trivial solutions, see, this is a system of equation in f phi and f psi. It's a system of equation. Okay, so for a non-trivial solution of the above system, we want the determinant above system. We want the determinant to be 0, right? One has the determinant of that matrix. So basically, what is it? This is phi x plus p phi z, and then psi x plus p psi z, and then you have phi y plus q phi z and psi y plus q psi z. This is equals to 0. Yes, and the thing is this, so this is basically just the theory of system of equation. So since for the non-trivial solution we need this, and this is exactly the relation which is written there. If you put it together, you see this times this and the minus this times this, if you put it together, this is basically this relation which is given here. So let's just call it star. So I don't know, maybe I can call this thing as triple star. So triple star is equals to star. Okay, so please check this part. You just have to multiply those two and put it together and you get this equation. Okay, so this is how you get first order equation. And then so we are going to end this video here. Thank you so much.